Right, grade 12s, welcome to our lesson today. We are looking at electrodynamics. So I am sure this is not a new topic to you. You probably discussed or made this topic in your grade 10 and grade 11 study. So right, we are here, let's delve into it. As an introduction, we'll look at electromagnetic induction. What is electromagnetic induction? How do we use it in our lives? Why do we need it? Okay, so you guys, I am sure, already know that when you move a conductor, okay, in a magnetic field, or rather, or move a magnet rather, in a conductor, a current flows in the conductor. So either way, you might move a conductor in a magnetic field, or you can move actually a magnet near a conductor or around a conductor. Current will flow through the conductor, and this principle is known as electromagnetic induction. Electromagnetic induction. That is how electricity is generated in the various power plants that we already know. We can talk of thermal power generation. You can talk of nuclear. You can talk of hydro power generation. You can talk of wind power generation. So the idea here is simply to move the magnet. So in this giant power generation station, what happens is the magnets are within a big turbines, and as the turbines are rotated around the coil, then electricity is generated and then it's transferred to all parts of the country where it is required. So let's take a pause right now and look at this short clip, which will just remind us how electromagnetic induction occurs.
Let us study electromagnetic induction by changing the magnetic field around a conductor. We have taken a bar magnet, a coil, and a galvanometer. The galvanometer is connected to the coil and is used to detect the current flowing in the conductor. Move the magnet into the coil and carefully observe the galvanometer deflection. As the magnet is moved near the coil, there is a momentary deflection in the galvanometer. As the magnet comes to rest, the deflection of the galvanometer stops. The deflection of the galvanometer indicates that there is some current flowing through the coil. The galvanometer deflects only when the magnet is in motion near the coil. Motion of the magnet is responsible for the changing magnetic field. This changing magnetic field is inducing the current in the conductor. This phenomenon is called electromagnetic induction.
Alright, so there we are. So we now understand, or we appreciate electromagnetic induction. So we have to move. In this case, in the video, you were seeing a magnet being moved. But as I said, when it comes to giant electricity generation plants, they move turbines which contain magnets around the core. So that is how electricity is generated. We are going to look at the generation of electricity at a little bit later stage, but for now let's just look at what affects this, how much electricity is produced, and other specifics that we might need to mention and understand when it comes to electromagnetic induction. So the amount now of the current will depend on these factors. The first is the speed at which the conductor experiences the changing magnetic field, and then the second one is the number of coils that make up the conductor, and then lastly the position of the plane of the conductor with respect to the magnetic field. So this is how it will look like. So this here is the bold line here is our coil. Okay, so when it is horizontal like this, and these are magnetic field lines going down, you can actually see that it is perpendicular to the magnetic field. Then the coil has to rotate, so as it rotates, it loses contact with some of the magnetic field lines until it becomes horizontal. And when it is horizontal like this, there is no flux that is cutting through the coil. Then it starts to descend again, and then the whole process continues. So it's a cycle that okay, so let's look at the result of this. So this is the effect of orientation of the conductor with respect to the magnetic field. So these are series of figures showing that the magnetic flux through a conductor is dependent on the angle that the plane of the conductor makes with the magnetic field. So the angle has got a lot of effect. So the greatest flux passes through the conductor when the plane of the conductor is perpendicular to the magnetic field line. So this is here. So when when the conductor, or when the plane of the conductor is actually perpendicular to the magnetic field line, that's where you see the greatest flux. Just look at the number of magnetic field lines. You can see that the most pass through when the conductor, the plane of the conductor is actually in this position. So the number of field lines passing through the conductor decreases as the conductor rotates until it is parallel to the magnetic field. So when it is here, as I said before, there is no flux that is passing through the conductor. So if the EMF induced and the current in the conductor were plotted as a function of the angle between the plane of the conductor and the magnetic field for a conductor that is a constant speed of rotation, then the induced EMF and current would vary as shown below. The current alternates around zero and is known as alternating current. So look at here, we've got EMF here. Guys, we know what EMF is. We talked about this when we're doing electrical circuits. This is electromotive force, which is also the voltage, and then there's the current here. So we can actually look at this. So it varies from 0 to a maximum. Obviously here when it is at 0, we are looking at a parallel, the plane of the coil or conductor being parallel to the magnetic field line. So there's no flux passing through there. So there's actually no generated EMF. Generated EMF is 0. Even the current generated there is actually 0. So as the coil starts rotating and until it gets here, we are here when it is actually in a perpendicular position, and the maximum amount of magnetic field flux is passing through the coil or the conductor. That's when we have got our maximum current and the maximum electromotive force. Then it descends as the coil starts to rotate and catching and losing contact with some more field lines until it gets to 0 again, and then it goes deeper down, remember, and then gets the maximum. So this maximum here is when the coil is on the other side, when the side of the coil is actually down. Then it goes up again until it gets to 0. So it's actually a sinusoidal wave, and then it is a repeating cycle. So this is how we will actually get our our EMF and our current when we look at how much of the EMF is produced and how much is the current is produced as the coil rotates within the magnetic field. So the EMF E induced is not E, actually it's epsilon, but let's just leave it for now. The EMF, which is epsilon, induced around a single loop of conductor is proportional to the rate of change of the magnetic flux, which is phi, through the area A of the loop. This can be stated mathematically as EMF is equal to minus n delta phi over delta t, where phi is B dot A cos theta. What is A? A is the area, and B is the strength of the magnetic field. So you actually see that phi is the strength of the magnetic field multiplied by the area. Okay, but then because the area is changing, that's where the cos theta is coming into. All right, so you find that when when there is a the coil is perpendicular to the magnetic field, we find that our cos theta becomes 0. That's how we actually get our maximum amount of electromotive force. Okay, so Faraday's law relates induced EMF to the rate of change of magnetic flux, which is the product of the magnetic field strength and the cross-sectional area of the field lines that the field lines pass through. The cross-sectional area changes as the loop of the conductor rotates, which gives rise to the cos theta factor. As I said, because the cross-sectional area is not constant, when you look here, so it's actually changing here because the cross-sectional area is the total area that the magnetic field lines are passing or making contact with the coil. So you find that there is maximum area here, and then the area starts to decrease until there is a 0 here. Okay, so this is why there is the cos theta. The cos theta here, when cos theta is 1, okay, when the area is when the cos theta is 1, we've got your maximum current, maximum EMF, and then when cos theta is 0, you actually have your minimum here at 0. So the area keeps on changing. That's why we have got a cos theta here, cos theta factor. All right, so this is theta is the angle between the normal to the surface area of the loop of the conductor and the magnetic field. As the closed loop conductor changes orientation with respect to the magnetic field, the amount of magnetic flux through the area of the loop changes, and an EMF is induced in the conducting loop. So in a nutshell, this is electromagnetic induction. So what is electromagnetic induction? This is actually the production of electricity by moving and or by making or introducing relative motion between a magnet and a conductor, or relative motion between a magnetic field and a conductor. So just that relative motion will actually induce a current in the conductor. What is inducing? Inducing is just causing. So it causes current to actually come into the conductor, and then the current can be actually channeled or conducted outside or to the load where it is actually needed to actually power up some appliances. Alright, so this is, guys, electromagnetic induction. Let's discuss further in the next presentation, where we'll look at the electromagnetic induction principle as applied to the generators and as applied to the electric motors. How do generators harness this concept, or how do generators harness this principle to give us electricity, and how do electric motors use the same concept to drive us around? Because when we talk of electric motors, we're talking about the motors in cars, in fans, in everything that rotates or moves. So for a car to move, there is an electric motor that is rotating. And how is it rotating? The rotation comes from the this same principle. Okay, so there is electromagnetic induction, and that produces electricity. And okay, let's discuss that later in the generator effect that is coming up.